Chapter 11 is also hydrocarbons, hydrogen and carbon. Now, the only other thing we introduced in Chapter 10 was the halogens, and that we'll also see in Chapter 11. But we're dealing with predominantly carbon and hydrogen. And but now we're into Chapter 11 is unsaturated hydrocarbons. All right, double bonds. And we've got three classes here: alkenes, alkynes, and aromatics. These are all unsaturated. Not all the carbons. Chapter 10, the carbons all had single bonds around them. So, in Chapter 11, oh, there we go. That's how I go forward and backwards. In Chapter 11, we're going to be dealing with double and triple bonds. And then aromatics, which kind of get in their own class. Double bonds are alkenes. So ENE means there's a double bond in that molecule. YNE, alkynes, means there's a triple bond. So we've got ethene or ethylene, ethine or acetylene. Now notice what this means, a double bond. It's a carbon-carbon double bond, or it is a carbon-carbon triple bond. So you're not going to find a methene or a methine that has only one carbon. So the simplest alkene is ethene, 2 carbons. You've got to have at least 2 carbons to have a carbon-carbon double bond. That makes sense? All right. So here's comparing now what you're familiar with, the alkanes. There's ethane. Here's an alkene, ethene. Now when you put a carbon-carbon double bond, that's 2 bonds. And remember, carbon only has 4 bonds. So 1, 2, 3, 4. It doesn't have 3 hydrogens around it. It only has 2 hydrogens. Sometimes what we'll see. So that's ethene, carbon-carbon double bond with 4 hydrogens. So what we're kind of looking at right there is this thing right here with 4 hydrogens on it. Yeah, it's good to get the model out here, because what you find in contrast right away, if we were looking at ethane here, ethane is a 3-dimensional, it's a 3-dimensional molecule. I don't have 2 of the hydrogens on there, but that's ethane. Ethene is flat. All 4 bonds are, all 6 of these nuclei, 2 carbons and 4 hydrogens, sit in the same plane. So we say that the atoms are planar around the double bond. All right, they're planar. And then I think I have a triple bond down in here. Yeah, haha. I don't only have a triple bond. I have acetylene. There's a triple bond, or at least the way the modeling kit would depict it. But what we've got here, 2 carbons sharing 6 electrons. 6 electrons being shared between these 2 carbons. And then 2 hydrogens, and it is linear around the triple bond. The 4 atoms, I don't care what 4 they are, whether they're hydrogen, carbon, carbon, hydrogen, or hydrogen, carbon, carbon, another carbon, or whatever you got around that triple bond, is linear for 4 atoms in a row, actually in a line. So the bond angle there is a 180-degree bond angle. The hydrogen, carbon, carbon bond angle is 180 degrees, and then another 180 degrees around this carbon gets this full circle. So that's linear. All right, so this is the one that's going to throw you off a little bit. And I've seen students so many times. I say, draw acetylene, and they draw this. Why? Because they go ENE, double bond. This is a common name. It's kind of a fluky common name. It has the wrong suffix on it. So it's acetylene is ethyne. It's a carbon-carbon triple bond. What is acetylene? What's that used for? For what?
It's used in like auto mechanics.
Yeah, how do auto mechanics use it?
Cut.
Welders. Some muffler shops, they don't, you pull in with an old car with a muffler that, the bolts are all rusted in there. Rather than try to get that muffler off, they fire up a welding torch and just cut it right off the car. Of course, they got a gas tank right there. So they got to know what they're doing, because they could just easily cut a hole in the gas tank. And what do they have? They got a welding torch sitting there. It's about as hot as it could be. But the girders in this building, welders pull down the welding mask and they're welding girders together. The girder comes in and they're welding it. What they have is a tank of acetylene gas, and they have a tank of oxygen. So acetylene burns pretty well, but it burns really well with oxygen, pure oxygen. So that's your welding gas right there, acetylene. All right, yeah, here's a bit about the bond angles. So I'm showing you that this thing is flat. This molecule is flat. And if we take a little journey around this carbon, take a journey around that carbon, there's a bond. To get a bond, you have to have 3 atoms. So it's a hydrogen, carbon, carbon. So I got a line there, I got a line there. What's the angle between those lines? 120 degrees. 120, 120 is 240, and another 120 is 360. We've gone around a circle. So that's what I'm talking about. There are 120 degree bond angles around a double bond. 180 degree bond angles around a triple bond. 109.5 degree angles around a single bonded or saturated carbon. It has 4 things coming out in 4 equal directions. All right, so the alkane is zigzagged. The alkene this is all flat. This is all flat, but then it becomes. Now you say, well, what is that? That's half alkane, half alkene. No, it's an alkene. One double bond throws this into this class. All right. What does it? This does not have a double bond. No double bonds here. It's saturated. This has 1. I don't care how long this thing is. This is an alkene. Because that double bond, you'll see as we get to the end of this chapter, can react in ways that a single bond can't. And if a molecule just has 1 of them, it can react that way. All right? So this is an alkene. And let's just take a look at that one. That's that part of it. But instead of coming over here to a hydrogen, we're going to come over to 3. We're going to come over to 3 carbons. So I need 1 more here. Take a look at that. Get our feet on the ground with alkenes. So there you go. That's got 5. The longest chain is 5 carbons. 1, 2, 3, 4, 5. This right in here, all of those atoms are in a plane. Even that carbon. I could slice a plane right through there. But then you see it becomes an this portion of it is saturated. I'm not going to call it an alkane. The rest of the molecule is saturated. This is unsaturated. And it's three-dimensional and zigzagged. But this is flat with 120-degree bond angles around it. So there you go. And that is, okay, now let's just think of our IUPAC names. What's the number one rule for naming in IUPAC? What's the first thing you figure out? The longest chain. 1, 2, 3, 4, 5. So that means it's a pent. So pentane, we're going to drop the ANE and add ENE. This is pentene. Now that's not the whole name. All right, that's not the whole name. Because why? Let's just write that down. Pentene. Let's write it right below this. Pentene. So we've got the pent tells us 5 carbons long. The ene tells us we got a double bond in there. Okay, what more would someone need to know to draw this correctly? Where the double bond is. This molecule is pentene. You see that? That molecule's pentene. 1, 2, 3, 4, 5. Pentene. But it's not that pentene, is it? So what we do here is we're going to start counting. Which end would you count from? What do you think is the most important end to start with? Yeah, the one closest to the double bond. That's what's really important in this molecule. We're actually putting it in the parent name, calling it pentene. So, boy, the double bond, that's the most important thing in this molecule. So we're going to call that carbon number 1, 2, 3, 4, 5. And so we're going to call this 1-pentene, 1-pentene. And what does the 1 say? We don't need to call it 1,2 because I know that a carbon-carbon double bond is between 2 carbons. Tell me where the double bond starts. Starts on the first carbon. That's all you got to do is tell me where it starts, and I can draw the molecule. Follow me? So that was that is 1-pentene, and this is actually 2-pentene. 1, 2, 3, 4, 5. It's not, look at this, 1, 2, 3. It's not 3-pentene. It's 2-pentene. 2-pentene. So we're going to start counting from the end that gets us to the double bond the quickest, and then we're going to just put the number for the first carbon in that double bond. All right. I'm probably getting ahead of myself a little bit. Okay, there is a triple bond. And let's just put that molecule out here. There's your triple bond. These always look like puppies. I don't know if that's a Dachshund, or whatever. At any rate, there's your triple bond. 1, 2, 3, 4, 5. Pent, again, longest chain. But now triple bond, ine, pentyne, and again, it's 1-pentyne. You see, so you're taking the rules that you learned in chapter 10, and we're just tweaking it a little bit. Now the other rule, well, we'll get into this, I think. We're just getting introduced here. But what I said a moment ago is that 4 atoms around a triple bond, 4 atoms are in a line. Now, not everything else is in a line, but those 4 atoms. the two carbons in the triple bond, the atom that's on the left, the atom that's on the right of that triple bond are all going to be in a straight line. All right, so even when you get down to doing line diagrams, we'll look at this stuff. But even when you get into line diagrams, you can kind of put these line diagrams similar to the shape of the molecule around that double and triple bond. All right, physical properties. Again, these are nonpolar. These are carbon and hydrogen, nonpolar bonds. They're very much like the alkanes. Alkenes will dissolve in alkanes will dissolve in alkenes. Alkenes will dissolve in alkanes. Why? They're all nonpolar. Like dissolves like. So they're highly soluble in nonpolar solvents. Again, melting and boiling points rise with increase in molecular weight. That's generally true. The different classes of molecules will start out at different points, but so you can't all say they're all have similar melting points and boiling points. You'll find alcohols will have much higher boiling points than alkanes, but as the molecular weight increases, boiling point increases. So alkanes, as molecular weight increases, boiling point increases. Okay, here are some alkenes up above here: ethene, propene, butene, 2-methylpropene. As you're getting up, as the molecules are getting bigger, they're getting heavier, and the boiling points are increasing from negative 103 to 7. 2 carbons, 3 carbons, 4 carbons with a triple bond in them. Boiling point is increasing as you get bigger. Okay, IUPAC names: ethane, ethene, ethine, propane, propene, propine. Now, I don't need a 1 in here. I don't need a 1. Sometimes people will put numbers on there, and it's not necessary. If a number is necessary, it has to be there, be counted off. Like, just to tell me pentene would be an incomplete name. But propene is a complete name because, I mean, if I drew it this way, if I drew it that way, just turn it around, drew it that way, where would you start counting? On the right? You'd start counting here. This is 1, 2, 3. Over here, we're going to start here. 1, 2, 3. So you can see all we did was just flip that molecule around. Okay? So the 1 is kind of unnecessary. And same way with the propine. Okay, number from the end that will get the first carbon of the multiple bond, the lower number. Prefix the name with the number of the first multiple bond carbon. And then prefix branch and substituent names as for alkanes. Okay, so if we get, well, let's see if we have some examples with substituents on them. Okay, here's an alkene. Let's look at that one. Name that top molecule. Longest chain? 7. All right, 7. Now, if I started over here, 1, 2, 3, 4, that gets me to that carbon on the number 4. But for example, if I start here, 1, 2, 3, I get to the start of that double bond on the number 3. So if I started here, 1, 2, 3, it doesn't matter. Either this or this is carbon number 1, and the other one is a substituent. So let's just call this carbon number 1, 2, 3, 4, 5, 6, 7. So since the longest chain is 7, and there's a double bond in it, what's the parent name? Heptene. And the double bond begins on what carbon?
3.
And what we left out of that name now is that we've left 3 carbons out of that name, a methyl group and an ethyl group. And which one goes first in the name? Ethyl. So you're all ready for that quiz. Should we have the quiz right now? No. Okay. 3. So it's going to be 3 ethyl dash 6 methyl. Now that's a Y, that's an L right there, so I need a dash to distinguish my methyl from my 3. I think that's the full name. We left anything out? That's the full name. 3 ethyl, 6 methyl, 3 heptene. All right, and this one is a neat little character. This helps us figure something out too. What's the longest chain here? 6. So and it's got a triple bond. So the parent name is what? Hexyne. So you're already speaking German. Hexyne. All right, now we could start 1, 2, 3. That would be carbon number 3, 4, 5, 6. Or we could go 1, 2, 3, 4, 5, 6. Which one do you think is 1? This one. All right, we're going to favor this one as 1. It doesn't matter for the triple bond. It's going to be a 3-hexyne. It's 3-hexyne no matter which end I start counting on, right? But if I start here, this is actually 1, 2, 3, then the bromo gets a lower number. It gets the number 2 instead of the number 5. And that's why we like that. 2 bromo dash 3 dash hexyne. Let me just modify that just a little bit. Let's say we had see, how do I want to do this? Yeah. Yeah, I'm trying to modify this a little bit here. Okay, let's look at that one. Okay, now what's the longest chain? 7. All right, so that's 7 carbons long, so it's going to be heptyne. Yeah, I'm trying to get you one here that kind of confuses us at first, saying, If I started here, that would give this the number 2, 3, but that would give this a number 4. If I start here, 1, 2, 3, it's 3 heptine. This takes precedence. You start from the end closest to this functionality, okay? I don't care about the substituents. You get the lowest number. It didn't matter over here because no matter which end I started on, it's a 3 hex sign. But it matters over here because I'm not going to call this 4 hex sign just to give this a lower number. I'm going to start at the end that gets me to the triple bond the soonest. So this is carbon number 1, 2, 3, 4, 5, 6. So this ends up being 6 bromo, 3 heptine. You see that? Okay. So the substituent, here we took the substituent into consideration because it did not affect how we numbered that functionality. But over there, we ignore it because we want the lowest number for the triple bond. Yeah, there you go. Those are the names. 3-ethyl 6-methyl heptene, 2-bromo hexine. Okay, name that one. Go ahead and name that one. Find the longest chain. Keep in mind that some of these have been chosen to, that they're a little bit potentially confusing. And they're there to clear up the confusion. Well, there are 2 ways I could ask about the longest chain here. I could just say, what is the longest chain? What's the answer to that question? 6, 7, 7. Or I could say, what is the longest chain that contains the double bond? How long is that chain? 6. That's going to be our longest chain. 6. Okay, well, this is there to help you see this. The longest chain has to include, if we're going to call this an alkene, if it's going to end in an ene because there's a double bond in it, then that portion of the chain has to contain the double bond. This can never be a substituent. Well, I won't say can never be a substituent. You can get into some molecules that are so confusing and have so many functionalities that somehow you have to deal with a double bond as a substituent. But we don't do that unless we have to. And we don't have to here. So in other words, I could go 1, 2, 3, 4, 5, 6, 7. That's the longest chain. But that has the double bond hanging off here, off the side of that chain. It's no good. So we got to be here, and we're going to call this number 1. We're going to start with the double bond. 1, 2, 3, 4, 5, 6. See, 1, 2, 3, 4, 5. That's just 5. But this is 6. So that's what we're doing here. This is carbon number 1, 2, 3, 4, 5, 6. Now finish the name. Parent name? Hexene. And the double bond begins on carbon number 1. And we got an ethyl on carbon number 2. All right, and then what do we do with our last two substituents there? 4, 4, 4. 4, 4. 4, comma, 4 dash dimethyl. All right, we got a di, so we need two numbers. 4, 4 dash dimethyl dash 1 dash hexene. And there's the name. You can see some of these molecules were hand-picked. Guess what? You can have two double bonds in a molecule. Two double bonds. Here's a double bond that starts on carbon number 2, 3, 4. Another double bond starts on carbon number 4, 5, 6. So it's hexene, but it's 2-4-hexadiene. So when you see diene in a name, di, you're using the di prefix like you would use it in front of dimethyl, but it's a diene. And you're putting two numbers there, and what are those two numbers? That's where each of those double bonds begins. Carbon on which each of those double bonds begins. 2,4-hexadiene. Yeah, I mean, there's others there, but we're going to come across something like this, butadiene. We're going to come across butadiene. Butadiene, what is it? It's like 2-methylbutadiene is what the sap they get out of rubber trees. It's a butadiene. And then they polymerize that into rubber, make rubber out of it. So we come across it. You can come across, same rules for alkynes. A lot in chapter 11, we're gonna concentrate on alkenes, and then sometimes we'll just say, well, alkynes, you would handle them very similarly. So if we had two triple bonds in here, it'd be 2,4-hexadiene. Diene, di, and a y after it. That seems like bad grammar or bad English or something. I'm not seeing a diene name. So, but you would use a similar thing, okay? There are cycloalkenes. Very first day of class, I said carbon is so versatile in making molecules. It has this 4 bonds around it, and I mean, just look at the stuff. This is like Legos. Legos are very versatile. I mean, you can make a Star Wars spacecraft, you can make a log cabin, you can make an airplane, anything you want to out of Legos. They're so versatile. Well, carbons are very versatile. They make hundreds of thousands of different molecules can be made out of carbons because they are so versatile. So here's cycloalkenes, and this here is trying to point something out to us. Remember, we had this kind of situation with cyclohexane. We had cyclohexane, and we had a chloro and a methyl group on it. But all the 6 carbons in here were identical. This would be cyclohexene. Cyclohexene. ENE. Cyclohexene. So what does that mean? We got a double bond. So what does that mean? We got to start counting somewhere around this double bond. That's where we got to start counting. We're not going to start counting at the chlorine so this could be 1, 2. We got we gotta, if we say 1 is where the double bond begins, we have to go in that direction. 1, 2, 3, 4, 5. Or we could go 1, 2, 3, 4, 5, 6. Okay, so if I went this direction, I get to a 4, 6 numbers for my substituents. 4-chloro, 6-methyl. But if I go this direction, 1, 2, 3 methyl, 4, 5 chloro, I actually get lower numbers. So I'm going to favor this. This is the correct name. This is the correct name because it is giving you the sum total, the lowest numbers for all the substituents. We don't have a 6. There's nothing on carbon number 6 if we go this direction. We're not saying we're going counterclockwise or clockwise. We're going to go in the direction that gives us the lowest numbers for the other substituents. Okay, now haloalkenes, haloalkenes. Yeah, haloalkenes. We've got either chlorine, bromine, iodine, fluorine, whatever. This, these are the haloalkenes here. Well, haloalkenes, haloalkyne, and here is just a dimethyl. Yeah. So 1, 2, 3, that's where I'm getting that 3 octene. On number 2 and on number 6, I've got methyl groups, so 2,6-dimethyl, 3-octene. 2-chloro, 2-butene. So 2-chloro, 2-butene. Okay, 3-chloro, 4-methyl, 3-hexene. So it's hexene, 1, 2, 3, 4, 5, 6. The ene starts on carbon number 3. You can see they're given precedence to the chloro group over the methyl. Otherwise, it would have started here, 1, 2, 3. It would have been 3-methyl, 4-chloro. But they've given the precedence, and we did that with the cyclohexane in chapter 10. We gave priority to the halogen over the alkyl group. Okay, now, take a deep breath, because we're going to get into something now that's very, very important and a little bit tricky. Cis and trans isomers. Very important and a little bit tricky. I told you back in chapter 10 that there is free rotation around a single bond. Remember that? Free rotation. These molecules, you can rotate around these single bonds. And when we had hexane, it got in all these different contortions, and actually the one end could come to the other end because it could rotate around. It was so flexible, spaghetti-like. All right, now, when we get to the double bond, what you need to start understanding is we don't have that free rotation. All right, here's 4 carbons. You say, well, that's up there. Let's get that down there. I can't get that down there. Even in this model, the way we have this, and it's not that we can't rotate because the model can't do it. It's when a carbon-carbon shares 4 electrons like this, it locks it into that position. Locks it right there. These are pi bonds. These aren't simple sigma bonds that these atoms are sharing 2 electrons and they don't care what's going on out here. These atoms are sharing 4 electrons, and the electrons are being shared up above and below the atom, and they just are set in that position. So there is not free rotation around a double bond. Well, what's the big deal about that? Well, what is that? What name that molecule? What's the longest chain? 4 carbons long.
4 butene.
So it's butene. And where's the double bond begin? 2 butene. So that's 2 butene. What's the big deal? It's 2 butene. Name that molecule.
2 butene.
2 butene. All right. Here's the rub. We've got two butenes, and they are not superimposable on one another. They are distinctly different molecules. So they are isomers, right? Same. I didn't take any carbons away, hydrogens away, didn't bring any in, so they have exactly the same molecular formula, but different structures, different geometries. They have different geometries. So they are geometric isomers of one another. I think there's a way for me to freeze. I thought I figured that out. Freeze my, oh well, let's not worry about it. So here's one of them. And right below it, let's draw another one. All right. They're both 2-butene. And these are the poster childs for this kind of isomerization. If you just think of butene with the double bond in the middle, you've got, if the methyl groups are on the same side of the double bond as they are in the top diagram, we call it cis, like same. Cis 2-butene. In the bottom one, you can see that the methyl groups are across from one another. If you make a phone call from New York to London, you're making a transatlantic phone call. Trans. You are calling across the ocean. Well, these methyl groups are across from each other in that double bond. The double bond in between them. Trans 2-butene, cis 2-butene. Okay, and they are distinctly different molecules. So you get cis and trans. And this is a consequence of the fact that the double bond, it restricts the rotation around that double bond. You would actually have to break, if you broke that double bond, even temporarily, you could flip it around and, reform it. Where in food labels do you see these words? Trans fats. No trans fats. And they're using the word just like this. What's that mean? Natural fatty acids that are in vegetable oil, canola oil, coconut oil, olive oil, the the unsaturated fatty acids that are in nature are cis. Cis double bonds in those unsaturated fatty acids. We'll study that really deeply in chapter 17. But you're hearing it. It's not like, oh, I wonder if they mean the same thing. Yep, they do. They mean the same thing. They're saying they don't have any trans isomers of those fatty acids. And they get those trans isomers from hydrogenation. They go in, so you get a cis, you start out with a cis double bond. And yeah, I'm getting ahead of myself. We'll get it in chapter 17. Otherwise, I won't have anything to tell you in chapter 17. So we'll get there. Okay. I gotta also tell you what your class project is. Don't at 10 after. I'm gonna tell you what the class project is before you leave today. Okay? All right. So make sure. Oh, I can't. I'm so glad I remembered that. All right. There's your two isomers. There's your cis, your trans. Okay. Now. Okay. What you got to learn now is you got a molecule with a double bond in it. Do I need to use the cis and trans in the name or don't I? Okay, there's times when you do need to use it and there's times it's not necessary. So that's what is going to be what we need to figure out now, identifying cis and trans isomers. All right, there's that slide. There's the gobbledygook that explains it. All right, let's take a look at a couple examples. Well, let's read that. If one end of the carbon double bond has two of the same groups, cis and trans isomers are not possible. So if you see what you're going to be looking at, you're going to focus on the double bond, and you're going to be looking. You're going to focus on the. Why does it do that? Focus on the double bond, and there's going to be 4 things around it. All right, so that's what you're focusing on. There's 4 things around it. If one of those double bonds has 2 things that are identical, then boom, it's not cis or trans. You don't need cis or trans in the name. We'll look at some examples. Both carbons have to have 2 different things on them, and then each carbon should have something that is the same as something that's on the other carbon. That's basically what this is saying. Both carbons must have 2 different groups attached, and then find a group common to both of the carbons. And if you got that, then you've got cis and trans. So let's take a couple examples. Try to apply that. So here's a molecule. There's your A, B, C, D. We're looking, there's the double bond, and here are the 4 things that are around it. So ask yourself, well, first of all, does either one of these carbons have 2 of the same thing on them? No. No, that carbon has a hydrogen and a methyl. This carbon has a methyl and an ethyl. Different. Okay. We might have cis and trans here. So each carbon has 2 different groups on it. Does the 2 carbons have some group that's the same? Yeah. We got a methyl here and a methyl there. All right, so this and this are the same. So A does not equal B, C does not equal D, A equals C. It is a cis or trans isomer. Now, where are those 2 things that are the same? Which side of the double bond? They're on the same side of the double bond. So what is this? Cis. Okay, let's carry this to completion right here. So we now know that it is a cis isomer. All right? Okay, now go back and say, what's the longest chain? What's the longest chain? 5. 1, 2, 3, 4, 5. Now, that could be a little confusing because I said, oh, that's a methyl substituent. That's not a substituent. That's now part of the main chain. Follow me? Even though it is a CH3, it is a CH3, and that's a CH3. They're the same, but in naming it, this is 1, 2, 3, 4, 5. So we're not going to call that an ethyl group. 5, that's pentene, right? Where does the double bond begin? On the second carbon, 1, 2. And what did we leave out? We didn't leave this out. That's in that name. We left that out. And where is that? Carbon number 3. And that's the name. We figured out it was cis. We figured out cis should be in the name. And then we went back and said, okay, what is this molecule? And we applied our normal rules. Longest chain, 5. Double bond begins on number 2. We left out that C group up there, which is a methyl on carbon number 3, and we got the full name. Yes?
What happens to the hydrogen?
We don't name hydrogens aren't substituents. You know, let's take that question. I've got 2-pentene, and it's cis-2-pentene, so I'm going to go like this. There's my pentene chain, right? And I've got a methyl here. And then what do? How do I finish off my structure? The hydrogens. Okay? So hydrogen is just something you add. They don't need to be put in the name. You use as many hydrogens as you need. How many hydrogens does that have to have? 3. How many hydrogens does that have to have? 1. We've got 1, 2, 3 bonds right there. Let me clean that carbon up a little bit. So that only needs a hydrogen right there. And we need hydrogens here. All right, now in chapter 11, when I give you homework, I want you to put in the hydrogens. Don't say, oh, he knows that there's only 1 hydrogen there. That's true. I do know that. But I want to know if you know that, okay? You need to demonstrate you know that you only put 1 hydrogen on that carbon. Yes?
So like when you're naming in order, how do you, so you're always going to do the cis for trans and the methyl and ethyl first before you even like say if it's like pentene. So you're always going to say that part first, right?
You could do it both ways, but we were analyzing this molecule to figure out whether that is even going to need to be in the name. Let me give you another example. We'll get some more examples here in a second. But let's do this molecule. There's pentene. Okay, now let's apply our same questions. Let's do the 3 questions. Does this carbon have 2 different things on it? No. You're done. You don't have to ask any more questions. Because the very first criteria for cis and trans is that both of these have to have 2 different things on them. So if you have a 1-pentene, which has 2 hydrogens right here, it's not cis or trans. Okay? All right? So that one is just going to be, let's just name it. This is carbon 1, 2. We don't have any substituents. So it's just going to be 1-pentene. It's not cis or trans. It does, even though this thing can't rotate, it doesn't need to rotate. There's a hydrogen up there and there's a hydrogen down there. If I rotated it, I'd have a hydrogen up there and a hydrogen down here. Rotating it wouldn't change anything. I can't rotate it, but they're both identical. You'd say, well, this hydrogen is trans to that one. Yeah. That hydrogen is cis to that one. Yeah. So it's neither. Okay, now let me make it a little bit more difficult. Let's pull that one right up there. Let's stick with that same skeleton. It's still one pentene, but I'm going to put a chlorine group here, and I'm going to put a chlorine group there. It's still one pentene. And let's start asking our questions. Does that carbon have two different things on it? Yes. Does that carbon have two different things on it? Yes. Do these two carbons have something that is the same? Yes. Uh-oh. We got 3 yeses. So it is cis or trans. What's the same? The chlorines. And where are they? They're on the top. So it is cis. All right? So this is cis, 1 pentene. And then what do we do with the chlorines? We've got a 1,2. A 1,2 dichloro 1 pentene. All right? So even though it is a 1 pentene, the double bond's on the end, that doesn't just wipe it away as, oh, I never have to think about that again. You have to ask these 3 questions in all situations. Does it have two different things? And that one does, and this one doesn't, because they're all hydrogens. You got it? Okay, let's see if you got it. All right. A. Decide whether each compound is cis, trans, or neither. Cis, trans, or neither. Trans. This has 2 different things on it. This has 2 different things on it. This and that are different. That is not superimposable on that. It's different. And it's going to be trans. Neither? Why? Does that have 2 different things on it?
Yes.
Does that have 2 different things on it? No. No. That's big and bulky and all, but that's exactly the same thing as that. So this is neither cis nor trans. You would just find your longest chain, wherever it is, and start naming the thing. Does that have 2 different things on it? Does that have 2 different things on it? Does each one of them have something that is the same? You got 3 yeses. And it's cis. Now let's name that one, because look at this. We got longest chain. What's the longest chain? It's 6. So it's 6 carbons. So the name is hexene. The double bond starts where? On the 3rd carbon. And you said it is cis. Period. The name hexene covered all 6 carbons. There are no substituents. There are no substituents there. Okay, I said you're going to get your prize. Okay, let me have your attention. I need to explain some important things about this project. Number one, you know what team you're on. You know the number of your team. And you're able to contact your team members. Okay, when you get this, is there 7 teams? Is there a team 7? Yeah. Okay. Okay, when you get this, you can see right down the left here, team 1, 2, 3, 4, 5, 6, 7. Okay? What your team is supposed to do is explained right there. So, kind of look at the overall project and then what your team's part in it is. Kind of glance down through this here, skim it, I'll try to explain it. Okay, let's follow down through here with me, and then what I will do, I'll put Chapter 11 homework back here as you're leaving. You can ignore it until after Wednesday if you want to, but if you don't want to ignore it, you got it. It's right here. As you're leaving, you can grab one of these, but let's look at this. Hypothesis. Are you hearing a lot about sugar in the media and all that? Okay. The types of sugars and the amounts of sugar in our average diets is having an adverse effect on our health. That's the hypothesis. So that's the statement I'm putting out there. Does the available information and studies support this hypothesis? If so, what are some of the specific conclusions that can be stated regarding either the type of sugar or the amounts and their effects on our health? That's what you're doing as a class. Assigned everyone. Well, it says photo several food labels with sugar in the ingredients. You can kind of do that. Start looking at what you're eating and drinking and look for sugar. Team number 1 is going to focus on what is sugar. Maybe give us a couple ideas and molecules of sugar, and then the many names of sugar that are in the diet. So the other teams, if you want to help them out, say maltodextrin, is that a sugar? Is cane syrup, think that's a sugar? Okay. Evaporated cane syrup, that's a sugar. All right, so there's all kinds of things that you find on a label that is basically sugar. Number 2, what are the dietary sugar recommendations from the World Health Organization, from FDA, from anybody else? Number 3, artificial sweeteners. Is that a way to counter the amount of sugar we're ingesting? Is that a good or bad way? What are the pros and cons? Team 4, how does sugar metabolize? Team 5, sugar and obesity. Is there a relationship? Team 6, sugar and diabetes. Is there a relationship? And Team 7, I've given you a website there. There is disease data by zip code for San Antonio, and you can kind of look at different diseases and maybe start seeing if there's any correlation, relationship, whatever. Okay. Now October 23rd. Today's the 11th. So in about 5 or 6 weeks, we're going to have a room reserved over there, and we're going to have a poster up and invite anybody to come in to hear our summary of this. So kind of put your information into 3 or 4 PowerPoint slides, every team, and we will combine it into one PowerPoint. And we'll probably go from Team 1 through Team 7 in our presentation. Okay? So that's what you're working on. I'll see you Wednesday.